today's subtopic, this idea of buffers. And in this, we've sort of combined two topics related to buffers, and that is this idea of titrations, where we're going to go through a buffer region, and then also what buffers are themselves. So let's look at today's challenge problem. So if we look, we want to calculate the pH of a solution that is 15 grams of HF and 25 grams of sodium fluoride in 125 grams of solution. So if we think about what we have here, and that is this HF, right? Once it dissolves in water, right? This is a weak acid, so it's going to donate its proton, and we're going to have this ion left, right? So if we look at what we have up here, right, we have some amount of HF and some amount of F minus. So because we have some of this and some of this, when we have a weak acid and its conjugate, let's go, it's a weak acid or a base, and the conjugate, we have a buffer, right? Which means that because they're both there, any changes in one is going to act or follow Le Chatelier's principle. So if we shift some of this over to that, right, equilibrium is going to try to reestablish by shifting some of that back, right? In which case, we can resist small changes in these concentrations is going to have a very small effect in that. So these buffers are going to resist changes in pH. Right? So we are going to allow these buffer systems are going to resist changes in pH because of Le Chatelier's principle, right? Both are there, so we're going to get any additional stress is going to cause that shift. It's going to shift in one direction, but Le Chatelier's principle is going to cause it to shift back, right? And the important thing is that we can define this pH using the Henderson-Hasselbalch equation, which is the pH is equal to pKa plus the log of that species, which is a base, divided by that species, which is an acid, right? So in this case, we are going to be looking at the pH is going to be equal to the pKa of the HF plus the log of the thing that is the base, which is the F minus, divided by the thing that is the acid, the HF, right? So we have to then take this information and calculate concentrations, because in this Henderson-Hasselbalch equation, we are going to go and talk about pH. So we know that we had 15 grams of HF and 25 grams of NaF. We have to get to concentrations. So we are going to then convert this. If we look at the molar mass of sodium fluoride, fluoride has a mass of 19. And hydrogen is about 1. So this is going to be approximately 20, right, for 1 mole. And we want a molarity, so then we have to divide by the volume. So the 125 milliliters is 0.125 liters. Right? And then we're going to do the same thing for this. Right? So 22.998 for the sodium. And then the 19 gives us 41.99, if we will, and for 1 mole. And again, to get to the concentration, we divide by the volume. So when we do this one up here, we get about 6.0, and down here 4.76 mole, right? And for this, the Ka for HF is 6.8 times 10 to the negative 4, right? I looked that up. It's a standard value, so our pK then, so our pH is going to be equal to pKa plus log, again, of the F minus over HF, which is going to be equal to a negative log of the 6.8 times 10 to the negative 4th, plus the log of the one that's a base, which is this one, 4.76, divided by the acid. So if we do this, calculate the pKa, we find that it's 3.17, right? If we look at this over here, right, we have more acid present than base, right? Which means that this number, the pH, should be lower than this number, right? If we have more acid, we should be shifting it towards the acidic side, which means the pH number should be going down. And if we do that math, plus the log of this becomes 0.791, our pH then equals 3.07. So we see that, in fact, it is lower in pH because we still have more acid, or lower than the pKa because we have more acid present than base. Right? And this gives us a segue into what we did in the lab this last time, where if we follow pH versus volume added for a titration, so if we're doing an acid we're taking something like HA plus NaOH, right? Then our initial pH is going to be low because this is an acid, right? So our initial pH is going to be below 7. And as we start adding this base, we're going to start increasing this concentration, or the pH. And it's going to go until we get to a point where it's going to jump up, and we're going to do this, where the equivalence point is going to be the inflection point here. Right? So if the HA is weak, right, then this point here, this pH is going to be a weak acid problem. Change the color. This is going to be a weak acid problem that we've done before, which is an ice table. Right? The region in here, this is going to be, we're going to convert it, some of that weak acid to conjugate base. This becomes a buffer. Once we get to the equivalence point, we've converted all of that weak acid to conjugate. So this becomes a, can't write today, weak base problem, where we do an ice table. And up here, the pH, the thing that's going to dictate the pH the most is the excess NaOH, right? So if we follow our titration table, we can see how we're going to address each one of these portions by looking at what kind of what kind of calculation we have to do to dictate pH. Okay. If we look at a strong acid, strong base titration, because those are strong, the conjugates are going to have no strength. At equilibrium, the pH is going to be 7. Anytime we do a weak something titration, weak acid or weak base, the pH will no longer, at equivalence point, will no longer be 7. If it's a weak acid, like in this case, the at the equivalence point, we've converted all of that acid to a base. So what we have in solution is a base, so the pH should be above 7. If we do a weak base, strong acid titration, then at the equivalence point, we've converted all of that acid to base, so our base, excuse me, to acid. So the acid is what we have left at the equivalence point. So for a weak base, strong acid titration, the pH at the equivalence point is going to be less than 7. Any questions about that? Any buffers are actually fairly straightforward as long as we can recognize it's a buffer. And that means that we have either a weak acid or a weak base and its conjugate. Questions?